the stuff we're discovering, it's tempting to say, oh, that must be aliens, because we don't have any explanation for that. But how do you know it's just not something that you've never seen before?
Prominent astrophysicist,
very knowledgeable in all things space.
Your brain is going to go all over the place.
Professor of astronomy from Columbia.
Yes.
David Kipping.
There's an object passing through the solar system right now, which is not a planet. We went through a list with things like carbon dioxide, ammonia, water, stuff like this. Do we see this? No. Do we see this? No. Do we see this? No. You have to rule out everything. Once everything's ruled out, then I'd be happy to say, okay, the only thing left is aliens at this point.
Most of the people who are on this planet, they're just so self-absorbed with their life, not the broader spectrum of things. Where do we come from? Ancient civilizations.
There was a NASA task force put together by one of my colleagues to study a lot of these UFO and UAP encounters. One of the highlights of that report for me was,
if there's one thing that you could have a definitive answer to, what would it be?
it's the question that really haunts me, and it's
Now, before we jump into today's episode, I just want to mention that this podcast is brought to you by me and everything that I have built to help you guys level up. If you want to transform your physique, build muscle, lose body fat, build strength, then you have the Thirst app. This has everything inside that you could possibly need to get yourself in shape, to hold yourself accountable as well. I also have the Digital Playbook, which is a step-by-step guide to help you guys build a following, monetize the following, and also build a strong personal brand. This is everything which I have done over the past nearly 10 years to allow myself to live a life of financial freedom and also geographical freedom. I can basically do whatever I want. Life is good. And I also have my newsletter, which has been revamped, where I'll share exclusive podcast insights, my raw thoughts on business, fitness, and much, much more. So if you're interested about any of those, check out the description. You'll find the links to all of them. Now let's get cracking with the episode. David Kipping, welcome to the show.
thanks for having me. It's really a pleasure to be here.
But you know what? I've done over 100 episodes now, and this is the first time I'm actually speaking about space and the universe.
It's about time.
I know,
It's finally come around.
It's a bit shocking, really, because I am actually, not that many people know about it, but I am into that kind of thing. Like I've spent a lot of time going down the rabbit hole, watching YouTube videos and just getting lost in the exploration of space, but I don't really talk about it too much. Firstly, because I don't really know what I'm talking about, but secondly, it's not really relevant to the type of content which I produce.
Well, it's fascinating. That's the thing about being an astronomer that's so fun. I get into a taxi and Uber ride, and whoever's in the front, they, as soon as I mention I'm an astronomer, they're like, really? I've always been interested in space. It's so common. Like that's one of the great joys of studying the universe versus, say, being an accountant or something, where as soon as you mention that, they're like, oh, they'll switch off space. Like there's a mutual vibe that we all have about that.
And you have gone down the direction of studying exoplanets.
Yeah. I mean, that's certainly been much of my career, and I think it has gradually spread out. The question of life in the universe has always fascinated me. Ever since I was a young boy, I've been fascinated by that question. And to me, the quest for exoplanets, which, just to put everyone on the same page, that's a planet outside the solar system. So we have 8 planets we know of in the solar system, or 9 if you count Pluto. There's some controversy there. But the planets outside the solar system, around other stars, those are the ones that we've been discovering, like over 5,000 now. Over the last sort of 2 decades, we've been discovering those. To me, the natural endpoint of that question has always been, do these worlds have life on them? And some astronomers kind of shy away from that, and they say, no, we're just interested in the geophysics or the planetary science. I'm like, no, it can't. Look, the interesting question here clearly is, are we alone? So my work has gradually bled more and more into that question as well.
And an exoplanet, it has to be orbiting a star to be classed as an exoplanet.
Well, that's an interesting question. Yeah, I mean, there is a definition that the International Astronomical Union, these bigwigs of astronomy, came up with, and there's 3 criteria, and they kind of came up with these criteria more or less to sort of kill Pluto as a planet. And one of those criteria is that you have to orbit the sun. So all of the planets we've discovered outside the solar system are not technically planets by this definition, but clearly that's absurd. So clearly the definition needs to be revised to include these. It's just, for whatever reason, that vote has never happened, as far as I'm aware. But I think these planets usually are assumed to orbit other stars, but they might not, Mike. They could be planets. In fact, we know of some evidence now that these exist, of planets which are just between the stars, planets which get ejected from their solar systems and are rogue planets, free-floating planets.
Is it moving, or is it just
Yeah, they're
Close.
flying very fast through space.
Okay.
And so they will, periodically swing past other stars. In fact, there's an object passing through the solar system right now, which is not a planet, but it's a small piece of ice and rock, most likely, this comet 3I Atlas.
Oh,
and
yeah.
this was ejected.
Which is traveling extremely fast.
Yeah, and people are very interested in this. It's been all over the news.
Mm-hmm.
And that is an example of something which presumably was born in another solar system and perhaps got too close to its Jupiter or its Neptune, and that kind of acted like a particle accelerator and kind of swung it out of the solar system, its solar system. It flew between the stars, and now it happens to be passing through our solar system, and in the future it may encounter other solar systems.
Mm-hmm.
And so there's rocks, there's ice, which is just between the stars, and so by extension we think there should also be planets, moon-sized things, maybe even Jupiter-sized things traveling between the stars as well.
Don't want a Jupiter-sized thing flying around at that speed, though, through our solar system.
Yeah, that would be really bad news. If 3I Atlas was a Jupiter mass object, it would cause havoc to us.
Yeah, that would mess up the gravitational spin of everything.
It would end us, I would suspect. Yeah, I mean, even if it didn't directly impact us, which 3 Atlas is nowhere near impacting the Earth, just the gravitational influence would be enough. I mean, people don't realize how delicately balanced even our own solar system is. We have these 8 planets, and they go around these near circular orbits. But, you may have heard of like the 3-body problem. There's a TV show about it. There's a book series about it. And it's kind of infamous that whenever you have 3 masses, it's very difficult to make predictions for the future. Mm-hmm. And it's like the butterfly effect. If you just perturb one of those planets, like you just nudge it a tiny bit, the predictions come out radically different in the future. Mm-hmm. And so it turns out for our own solar system that if you run the clock forward about 1 billion years and you ask how stable is the solar system, in about 1 in 100 of those simulations, the solar system becomes unstable. So even our own home, as stable as it seems to us, is not guaranteed to be stable forever.
Yeah.
And so it makes perfect sense that there should be plenty of unstable systems out there. And these planets, they're flinging around. And if one of them went through our solar system, a really big one, man, that would be a very bad day. We could probably end up being ejected ourselves into deep space.
Yeah. And speaking about the stability of our solar system, if you were to think about a grand scale of things, what would actually happen in the long run? Like, would the Earth slowly stop spinning, and would the sun eventually just die out? Like, is that the end scenario? If we were looking at the grand
scale? Yeah, I mean, you're kind of on the right track. There's a couple of aspects there. So there's the orbit of the Earth around the sun. That's probably not going to change too much. So we're about 1.5. 1.5 times 10 to the 11 meters. So 150 billion kilometers from the sun. That distance probably isn't going to change too much. The spin of the Earth is changing, and that's due to the moon. A little bit due to the sun, but mostly due to the moon. So the moon, and we know this actually, people talk about conspiracy theories of did we land on the moon and stuff. And I always like to point this out. Like, there is a mirror on the moon that we put there. The Apollo astronauts put it there. And we bounce a laser off that mirror on a regular basis, and we time how long does it take the laser pulse to hit the mirror and come back. So we can measure really precisely how far away the moon is. And it's moving away from us. It's not in the same place. So about 1 inch per year, it's moving, it's receding. And so as a result of that, it's kind of stealing angular momentum. And so the Earth is slowing down in its spin. So if you go back in time, the moon would have been closer and the Earth would have been spinning faster. In fact, if you go back to when the Earth was first born, 1 day could have been as short as 3 or 4 hours when the Earth was first born. And it's been slowly spinning down. I think that's wild because animals and creatures that would have been living on the Earth in the past, their entire cycle would have been different.
Imagine looking up and just seeing the sun like literally move.
Just sweeping over. Yeah, it would have been pretty wild and there are probably exoplanets where this is very common as well. So the Earth is slowly spinning down. It will eventually tidally lock to the moon. So they'll both basically orbit the same speed around each other. So if you think about the moon's rotation period, it's currently about a month around the Earth. It'll go a little bit further away, maybe like 2 months, and the Earth will eventually lock to that period. So eventually 1 day will be about a couple of months. However, that'll happen if you calculate how long that takes. It's like 100 billion years or something for that to happen. Really long time. Way before then, your other point was more accurate. The sun will die. Yeah. So the sun's not going to last forever. It's burning hydrogen fuel, and it's eventually going to run out of fuel, just like we're going to run out of oil on the Earth if we keep burning it. So there's eventually going to run out of this supply. And that should happen in about 5 billion years. It will start running out
So
of
we're
fuel.
okay right now.
We're okay for a while. Although probably, I mean, the sun is actually, even though it's going to be stable for 5 billion years, it's been gradually getting warmer and warmer, or really more luminous, I should say, over time. So again, if you go back in time, when the Earth was first born, the sun was about 30% less luminous than it is today.
Okay.
And it's been gradually getting brighter, 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 brighter. And it's causing, it is a very small contributor to climate change. I mean, this is a tiny, tiny effect compared to what we're doing to the atmosphere.
Yeah.
But it is contributing. And so if you go forward to 1 billion years into the future, no matter what we do, as in terms of burning whatever chemicals we want, the Earth will become uninhabitable to complex life in 1 billion years, not 5 billion years, 1 billion years, just due to the sun getting more luminous. It'll still be there. It'll still be a normal star. But as it just gradually warms up, it'll push us over the edge. And all complex life, maybe microbial life will survive, but complex life like me and you, that's game over.
So all suns do this. They have a life cycle where it will have the peak luminosity. Is that the right term?
Yeah.
And then it will die.
No, they just keep going up. It's not they don't go up and go down. I guess eventually when they completely die, they go back down again. So it goes up and up and up and up. And eventually once it's run out of its 5 billion years of fuel, it then enters this giant phase. So eventually the sun will, when it's really running out of its hydrogen supply, it gets desperate. And in the core, it's essentially run out of fuel, and the only hydrogen that's left is on the outside. And so you can kind of think of the sun as almost chasing the fuel, and so it just gets bigger and bigger and bigger, trying to chase that remaining fuel. And it will eventually get so big, it will probably engulf the Earth. So in about 5-6 billion years,
it will be that.
It'll be that big. It'll be the size of a solar system.
Wow.
And some stars get even bigger than that. Some get as big as like the orbit of Neptune. So they get incredibly large. There's some wonderful, if everyone's never seen these YouTube videos, there's some crazy YouTube videos where you do size comparisons.
Yeah.
And you have like the Earth and it goes up to Jupiter. And then you go from Jupiter to the sun. And then you go from the sun to the next biggest star. And every scale up, your mind is just being blown by how much bigger the next thing is. So stars can get truly gigantic, and it's terrifying when you think about how large.
Well, I've seen the comparison of stars and also of the black holes, like how big they can get.
It means there's like some supermassive black holes which are 1 billion solar masses, and I mean, just the existence of those is baffling. How was it possible that 1 billion stars worth of material somehow all coalesced into this object? And it did it within the time period that we've had. I mean, the universe is 14 billion years old. That seems a lot, but that's a lot to happen.
How do we know that?
How do we know the age?
Because, when we're talking about ages of like the Earth, the solar system, the universe itself, like we always say like 14.1. Like how do we know exactly like to the point? The age.
This is the era of precise cosmology, as we call it. So in terms of cosmology is the study of the nature of the universe itself, whereas astronomy is more focused on astronomical objects like stars, galaxies, things like this. So cosmology cares about the shape of the universe, the size of it, the expansion of it, these kinds of questions. And so the easiest way, or the simplest way to imagine getting the age of the universe is it kind of connects to the idea of the Big Bang, essentially, the expansion of the universe. When we look out and we see these very distant galaxies that James Webb and Hubble have been observing, we notice that all of them are moving away from us, all of them. And we can tell this because they're very, very red. So just like a siren, a police car going by, the pitch seems to increase as it's coming towards you and decreases as going away from you. The pitch of light of all of these galaxies has decreased so much they're all very, very red. In fact, some of them are so red you can only detect them with infrared cameras. You can't even just see them invisible anymore. That's why James Webb's so powerful for finding those. And so we can tell from that redness their speed, and we notice that the further away they are, the faster they are moving away from us. So you can make a graph, and it's called the Hubble diagram that Edwin Hubble famously made about a century ago. And he just plotted, how far away is the galaxy and how fast is it moving? And when you do that, you get this kind of perfect straight line. And so that's called Hubble's law. And it tells us that the simplest explanation is that the universe is expanding in all directions. There's no center, because from another galaxy's perspective, they would see the same thing. Everyone's moving away from them. And once you've got the speed of expansion, you can reverse the clock, and you can say, okay, if everything's getting bigger and bigger, how long until everything was just all together? And
Mhm.
that's the age of the universe that we come up with. That, I mean,
Now, is that what you believe, that there was once nothing and then all of a sudden there was a bang?
I think if we're going to be like strictly talking in terms of the data and what we know, rather than just
Which is what you have
yeah,
to do. You
well,
can't say what
I'm trying,
you like.
Yeah,
What-
I'm trying to like delineate that a little bit. We don't know really what the nature of t equals 0 was. So, time equals 0. What happened at the very, very beginning? We know that you can run the clock back, and we know there was a certain point where the density essentially goes to infinity, that everything would have been stuck together. And it wasn't just all in one place, it was everywhere. So we think the universe is probably infinite. So in all directions, the density was just infinity, which is mind-boggling to think about. And the problem with that is that none of our mathematics, our physics makes sense. Once you get to infinity, nothing makes sense. So I think a lot of physicists aren't comfortable making firm statements about what the hell was going on as you get closer and closer to that time. Probably the best we can do is say what was happening at sort of 1 nanosecond after that point. But before that point, we just don't know. Maybe there was a previous universe before that, and it had collapsed down and it had gone through its own sort of big crunch that then bounced and caused a big bang. Maybe there was a multiverse of universes that sometimes collide together, and those collisions are the things that kind of ping big bangs. So there's lots of ideas. It's almost impossible for us to test because we don't have a time machine. We can't go back and really see what was happening. So this is where kind of the rubber hits the road of like, how far can science go? And I think asking questions about what happened at the very, 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 very start is incredibly intriguing, but it's probably the limit of what we can really do as science.
Is there, if there's one thing that you could have a definitive answer to, what would it be? Like you could ask one question and you can get the answer back.
So this is a bit deep and metaphysical, but it's a question that really haunts me. And I did do a video about this a while back, and it's, why is there anything? Why is there anything at all? The universe has all this mass, all this energy. And you might be able to reason that the Big Bang happened for some reason. Maybe we don't know what that reason is, but maybe one day we'll discover that reason. Maybe one day we'll be able to come up with an equation that says something really simple, like A equals B times X. And once you really understand that equation, you're like, I get it. This explains the universe. It explains the laws of physics, explains everything. And so maybe you might be satisfied with that, but I still wouldn't be satisfied with that, because why even have that equation? Because that equation itself, you think of it in terms of writing it down on a piece of paper into a computer program, it represents information. So where did that information come from? Right? Because like who put that there? That's really bizarre. And you can say, okay, maybe a god did it, or maybe we're on a simulation, the simulators did it or something. But you just get the same question come up again. Okay, what just define the parameters of that thing ahead of it? So it's infinitely
pretty weird
perplexing.
when you think about it.
Yeah, because it really just having absolutely nothing at all. We always talk in science about Occam's razor. The simplest explanation is the right one. And by far the simplest explanation, or the simplest outcome, I should say in this case, would be there was just nothing. How do we have all this complexity? We have microphones, we have me and you, we have all this biochemistry, we have stars, we have galaxies, we have all this ridiculously complex physics. That is bizarre. It would be far simpler if the universe was just a very, very boring place, or no universe at all.
Yeah.
And that is the question I think will haunt me my entire life. And I suspect it's simply beyond my comprehension to understand it, and perhaps humanity's comprehension. I mean, we have to accept we are basically walking primates. Why should we expect the universe to be comprehensible to us? There's probably things that, no matter how clever a human being is born, or augment ourselves with AI, whatever we do, there's probably some questions we'll never be able to figure out. And that's frustrating, but I guess something you have to accept.
It's weird as well when you think about, at some point on this planet, there was no life.
Yeah.
But there was the oceans. There was, I don't know, there probably would have been trees before there was actual organisms. And then at some point, somewhere, these organisms came to fruition.
Yeah, this is the process of abiogenesis. It's the technical name we call this. So the kind of the spontaneous emergence of life. That date at which it occurred is really early in Earth's history, which is the most interesting thing I think we can say about abiogenesis. So it appears the oceans probably formed on the Earth. The Earth formed about 4.5 billion years ago. So the timeline is the sun formed at 4.6 billion years ago. The Earth formed about 4.5 billion years ago, so 100 million years later. And then at about 100 million years later after that, as soon as the Earth has formed, I mean, when the Earth formed, it would have been just a ball of lava, right? It would have been like
hectic.
It would have not been a pleasant place to be in. It would have been bombarded with rocks. It would have been like Mustafar from Star Wars or something, right? Just a lava world. And yet, 100 million years after calming down, chilling itself out a bit, we start to see evidence for oceans. So we can tell that by the certain minerals that only form in the presence of water, and we can radiometrically date the age of those minerals and tell that, yes, there must have been water of some kind on the Earth pretty early on. And then 200 million years after that, we actually have evidence for life on the Earth, which is just like a blink of an eye. And this is not just like the first life, this is a biosphere already at that point, right? So there's life everywhere on the Earth after 200 million years. That is fascinating. And it's really perplexing, as you correctly point out, as to how it happened, because we have been trying in a laboratory, many laboratories across the world, to create life from scratch. Let's take the ingredients that we think should have been present on the Earth in that early time and even try and subject it to lightning and ultraviolet radiation and the different environmental conditions that we think were present on the Earth. And no matter what we do, we can't get anything close to life. We can get very simple organic molecules, amino acids, no protein. No one's ever known to make a protein in a laboratory just from raw materials from scratch spontaneously. We have to use pre-existing like enzymes and biological processes to catalyze that reaction. But that's kind of a chicken egg then. How do you get the first proteins and the first DNA and the first cell membranes? All of that stuff is just very, very perplexing. And it seems like a lot of stuff has to happen almost quasi-simultaneously. So the origin of life is a huge mystery. I think in this era of AI, of growing intelligences in terms of computation, it's potentially going to have a breakthrough there if you're optimistic. If we can simulate these chemistries in a computer rather than having to do it in a laboratory, that would greatly help. Because, of course, we can only do an experiment for maybe a year or two if you're very, very patient. You can't do it for a million years. A billion years is probably a short time by the Earth standards, but for us, it's a vast time. If we could do these laboratory simulations on a computer, we could probably speed that up then and imagine what it would be like to do 1 million years or 10 million years. And maybe then life might start in the computer, so to speak. So I'm optimistic we'll eventually be able to figure out a little bit more about this problem. But for now, it's incredibly perplexing. We just have us. Or, there's lots of life on Earth, but as far as we can tell, all life on Earth is related. Or, we are all brothers and sisters of each other, not just to other humans, which I think is a profound realization just socially, right? Every time you see another human being, wherever they are on the planet, they are essentially one of your kin, right? That's unambiguous. But it's also true of even, a ferret or a tree or an amoeba. All of us are interrelated to one single ancestor, as far as we can tell. And so that's interesting because it means if life did start a second time or a third time, maybe it did, it couldn't compete, right? So it's kind of like with anything, like if you get a big head start over somebody, it's pretty hard to catch up. And so if life started maybe 1 billion years later, a second time, it was too late. Life could be starting on my fingertip right now, but there's so much life all over our planet that will just gobble it up straight away. So it just can't compete. We are extremely well adapted machines to this environment, right? It's kind of crazy. You can walk outside in a t-shirt and feel comfortable because our bodies are perfectly adapted for this environment. And that is the product of billions of years of evolution.
So, in your opinion, what is the likelihood that there is something else like this planet that exists?
Yeah, it depends exactly how similar does it have to be? I think that's the big question.
I guess you'd be looking for a planet with water. Is that one of the key ingredients?
That would be great. Yeah, NASA for years has had a policy called follow the water. Yeah. And so that's been, because, come back to life on Earth, all life on Earth requires water to survive. There is no organism on Earth that can survive in the total absence of water for its entire life cycle. At some point in its life cycle, it has to have water involved. They can survive maybe months desiccated, but at some point, the water has to come back, otherwise it's going to die. So for that reason, we've chased water across the universe, and we see it. I mean, water is actually a very common compound to find in the universe. So it's hard to see it in liquid form on planets. We've never detected liquid water on a planet, but we've detected steam. We've detected gaseous vapor water in other planets, even in gas giants, Neptunes, and some super Earths and sub Neptunes. I think there's some evidence for water vapor as well.
Super Earth?
Yeah, good question. A super.
Sounds cool.
We don't know either. Actually, it's we're not even sure. But it's a planet that's in between the size of the Earth and Neptune. So the Earth is the Earth is
and Neptune is how many times bigger than the Earth?
4 times.
Okay.
Yeah, so it's something that's about 2 to 3 times the size of the Earth, and we just don't know what that is. Some people call them super Earths. Some people call them mini Neptunes. It depends, like which way around you go. We don't know which one they truly resemble. There's probably a bit of both. Probably if you're 1.5 times the size of the Earth, you're probably a rock. But if you're 3 times the size of the Earth, you're probably more like Neptune. It's really interesting to wonder what happens in that in-between space. Like, where does the crossover happen?
Well, that's probably where physics gets a little bit weird.
Yeah, super weird. There's ideas that there could be like ocean worlds in this in-between space, for instance. So some people call these Haitian planets. Haitian, I think, like Xi'an. So Xi'an is ocean, and then Hai is like and hydrogen atmosphere around it. So those planets...
you said those ocean worlds are actually harder for life to form.
They could be, because if you're totally ocean... it's very, there's going to be hard for organic molecules to come together at random and form these abiogenesis steps. So how do you get stuff to concentrate? Because if you want to start life, you need lots of complexity, complex organic molecules to come together in one place and do their thing. And it's hard in an ocean to do that, especially if it's a vast ocean that's hundreds of kilometers deep and spans a huge planet. 2 molecules come together, it's just unlikely. You're in a 3D volume. So we think it's easier if you have a surface, because then it's a 2D volume, right? Because now everything's concentrated. There's no height anymore. Everything's flat on the surface. So all you have to do is move in these 2 directions to come together. So generally, we think in chemical terms, maybe having some kind of land surface, or maybe a shallow ocean. So there's a ocean bed where things can concentrate. Those would be helpful for having the origin of life. So we don't know that. That's just speculation. It's reasonable. It's an educated guess at this point, but life might surprise us. We might find that there's life teeming in these oceans. We have 2 in our backyard, kind of, Europa and Enceladus, which are definitely not the size of these super Earths. They're much, much smaller. They're about 20% the size of the Earth. But within that icy crust, there's almost certainly a liquid ocean. And that's pretty exciting. There could be life in our own backyard. And if there was life there, it would be the most interesting place to discover life in the solar system, in my opinion. If we discover life on Mars, that'd be cool. It would be huge. But I think in my mind, I'd always wonder, is that our cousin? Right? Because we know that Mars and Earth exchange material quite regularly. Meteorites can get knocked off. Life can hitch a ride. We've already sent tons of probes there, which are contaminated. So we know there's material being switched between them. Europa is not only so far out, but encrusted in this encasing of ice that it's very difficult to imagine how an Earth microbe could have possibly hitched a ride, gone all the way there, penetrated 10 kilometers of ice to have contaminated that ocean. So it's a pristine environment. And, I would love to put a periscope down there. Right,
have you seen Europa Report, the film?
I think I saw the trailer. I don't think I saw the movie.
Yeah, so I think they eventually got onto the moon, and then they dug down, and then when they got there, they found like these mad creatures just swimming around.
That's what I hope.
Yeah.
It'd be fun. It could be a horrifying idea as well. But one of my colleagues, Rebecca Oppenheim, always jokes that this would be the place where the billionaires will want their sushi from. Right? Like, imagine you're someone's, you're at Bill Gates's dinner, and he serves up, by the way, this is sushi served from Europa. Like, oh, that's impressive. Right? That's the most likely reason we would go there in terms of finance.
So, if from what you're doing, you're trying to find these other, I guess, Earth-like planets. What are the tools that you are using to do that?
Yeah, so
And the various different methods, because obviously you can go by pictures, but then there's also detection of heat, infrared,
good
methods.
So to take a photo of another Earth would be the dream. We've not been able to pull that off yet. The problem is that the Earth compared to the sun is 1 billion times fainter if you take a photo.
Yeah.
So you don't have cameras that exist yet that can resolve that kind of contrast difference. It's just too much. On top of that, they're really, really close to the star. I mean, it doesn't seem like it from our perspective, but when you go light years, tens, hundreds of light years away, that tiny separation becomes indistinguishable. You just can't resolve it. So it's like trying to resolve the difference between the fingers of the Statue of Liberty from, the other side of the Earth. Like, you just need a camera that has such incredible resolution, but to distinguish those minute differences. So we're working towards building a camera that can do that, and the current name of that is called the Habitable Worlds Observatory, HWO. It's a bit of a mouthful. I think eventually
that's the name of the new camera.
Yeah, well, the new telescope.
The telescope.
Yeah, so
the most recent one is the James Webb.
Yes,
and that went out 2021.
Yeah, and the
one before that,
the
was
HWO
Hubble.
is not built yet. This is just a concept.
Oh, okay.
So this is like your concept car. This is like what we would like to be able to do one day. We've only recently just got James Webb out the door, and that thing cost $10 billion, which even by NASA's standards is a ton of money to spend. And HWO would almost certainly cost even more than that. So James Webb and previous missions, they don't have the ability to detect Earth-sized planets in terms of direct photographs, but they can still see them, just indirectly. And so the method I've been using for most of my career has been this transit method. So that's pretty simple. You just imagine, okay, even though I can't directly see the thing, it will sometimes, if it has the right alignment, it will sometimes orbit in front of the star and block out some of the starlight, just like a lunar eclipse or a total eclipse. So during a total eclipse, the moon completely blocks out the sun. But there's also the transit of Venus that some people have seen, or maybe not the typical layperson has seen this because you need a telescope to do it, but you can see the transit of Venus occasionally in front of the sun, Mercury too. And we're using that same technique. As this planet passes in front of the star gets maybe 1% dimmer. If it was a Jupiter-sized planet around the sun, it'd be about 1% dimmer for a short amount of time. Our cameras are definitely capable of detecting 1% changes in brightness, much, much better than that, in fact. And the Earth blocks out of order of 84 parts per million. So a tiny, tiny amount, where parts per million is literally 1 in a million. So that's a tiny, tiny dip, but James Webb is certainly capable of seeing that as well. So we've detected, I'd say, of order of hundreds of Earth-sized planets at this point. Many of them are indeed at the right distance from their star to be where liquid water could be on their surface. We've never done this for a sun-like star, though. So a probably surprising thing many people don't realize is that the sun is kind of unusual. And this is something that keeps me awake at night as well. Like, why do we live around this star and not another star? The most common star in the universe is a red dwarf.
Yeah.
They make up over 75% of all stars in the universe. We don't live around one. The sun is like a 10%er type star.
A red dwarf is cooler,
smaller, and much longer lived. They will live, our sun will die, as I said, probably in about 5 billion years. These things live for trillions of years. They'll be the last stars left in the universe. They'll go on and go on and go on. They're like the Duracell bunny. They just keep going. And so those stars, because they're smaller, and we're looking
closer.
The planets have to be closer, correct, for liquid water. So it's like the campfire, you have to get closer because it's a dimmer campfire to stay warm. But also, from the astronomy perspective, it's easier for us to see them because the star is smaller. An Earth-sized planet will necessarily block out a larger proportion of that disk, a larger proportion of the star. If you make it half the size, then the same size planet will block out 4 times more light by the rule of areas. So that means it's 4 times easier to detect them. So we found a whole bunch of those, and they appear quite common. About 1 in 6 of these M dwarfs, as we call them, these red dwarfs, have Earth-sized planets at the right distance for liquid water. So that's a lot. And there's been a huge effort to try and use James Webb and other telescopes to see, can we detect the signs of life in the atmospheres of those planets. And we can kind of just about start to do that experiment, which I think is pretty exciting because we've, for hundreds of years, thousands of years, humanity has been asking this question. And now finally we live in an age where we can actually do an experiment that can test it in some limited regime, but still start to give our first clues. And so far, there's been a couple of claims. People are arguing about those claims. We can talk about that more, but I don't think we have compelling evidence yet for a slam dunk detection of life elsewhere.
What would be a slam dunk detection?
That's also controversial, is what that would look like. I think different people will give you different answers. For a long time, we thought, we think about this pretty simply. We know the Earth has oxygen in its atmosphere, and oxygen keeps us alive, of course. We breathe it in, we need it to survive. We need it for our metabolism. But that oxygen shouldn't really be in a planetary atmosphere. If you took all the life away, it oxidizes things, it rusts, it reacts with things. Oxygen is a very reactive element. That's why we use it for metabolism. So if all life disappeared on the Earth, after about 1 million years, there'd be no oxygen left on planet Earth. You need a continuous supply of it, which is the trees, which is plant-based life on the Earth, which is producing it. So if you see oxygen on another planet for a long time, we thought that's life, because that's what happens here on the Earth. And then we started to realize that things are a bit more complicated than that. And we started to figure out, actually, there are some weird scenarios where oxygen can be produced without life. And then we started to scratch our heads and think, hold on, what is really a unique signature of life after all? And then there's the people who start to say then, okay, maybe it should be, you need two things. You need oxygen and, say, methane, because methane is also produced by life on the Earth. And then, again, people have been pointing out, well, maybe there's a way you can get both of these through strange ways. So the challenge of looking for life is that you're looking for something which we don't really know how it behaves, right? We've only got ourselves as an example. We don't know how alien life behaves. It could be completely different. And then on top of that, we don't know all the laws of science yet, all the laws of physics. There could be physics we are yet to discover. And this has been a big problem alien hunting for a long time, especially technological aliens. We started to see weird stuff in the universe. A good example is pulsars. Pulsars are these fastly rotating neutron stars. So they're almost a black hole. If you put a bit more mass on them, they'd collapse into a black hole. They're kind of the stage prior to a black hole, if you like. And these objects, when they collapse down, they're basically a giant atomic nucleus. They're about 10 kilometers in size, the size of Manhattan. But they're the mass of an entire star, just collapse down. One spoonful of it would weigh like the Mount Everest, it would be ridiculously dense. These are very strange objects. No one really predicted their existence. And then when we started to first detect them, they have these giant jets of radio energy coming out their poles, and they're spinning the same speed as a blender. In some cases. So, turn your blender on, spin 1 million times per second or something, and they can spin that fast. So when we first started to detect them...
That's mind-blowing.
Right. No one thought that was possible. It just seemed crazy. But what you saw as an astronomer was beep, 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 this radio ping coming at us, very regular, very controlled, very narrow band. And all of that looked like an alien signature. Mm-hmm. And so actually the first ever pulsar detected was not totally seriously, but quasi-seriously, called LGM1, Little Green Man 1. So that was its moniker for a short time within the team. It was Jocelyn Bell Burnell who first detected it. And so that goes to show you that, we just didn't have all the physics figured out yet. And so when you see something new, it's tempting to say, oh, that must be aliens, because we don't have any explanation for that. But how do you know it's just not something that you've never seen before? And I think that's true of the UAP stuff as well. There was a NASA task force put together by one of my colleagues, Dave Spergel, in Princeton, New York, and he came up with this. He came up with this report. He brought together many scientists to study a lot of these UFO and UAP encounters, and it was commissioned by NASA to investigate this. And one of the highlights of that report for me was talking about this thing called sprite lightning, which maybe you've never heard of. I certainly hadn't heard of it when I first saw it. I haven't heard of that. It's upside down lightning that's red. So it's very, very fast, happens much quicker even than lightning. And so pilots had been claiming that they were seeing this in the upper atmosphere for decades, and nobody believed them. They were like, how can there be red things just going upside down in the atmosphere. What are you talking about? It's,
So this is coming from where, not the ground, but
it comes from it starts in the
somewhere in
stratosphere.
the atmosphere.
Yeah, it starts in the stratosphere and it goes up. It's really strange. The physics of it, even now today, isn't completely fully understood. But these electrical discharges basically go, they look spectacular. If you ever see them, I recommend people to Google this red sprite lightning. They look like almost jellyfish or something, tarantulas going like up into the sky. They look so strange. And people didn't believe them. And then finally, once cameras got fast enough and sensitive enough, we started to capture images of it. And then people realized this thing was real. So even in our own atmosphere, fairly recently, the stuff we're discovering that we thought we knew all the physics of our atmosphere, and we're still discovering that it does stuff that we don't understand. I think that's the problem as an alien hunter. If you see something weird, how do you know it's not just something you don't yet understand?
Yeah, that's a very good point.
So that's the challenge.
Yeah.
I'm thinking about that very hard. I don't really have a great solution for it at this point, but it is, I think, a real problem the whole field has to think about.
So if, let's say, for example, there is something closer to home, maybe on Mars, there is a proven slam dunk existence of life.
Yeah.
How do you think we take that news, humans?
How
does it affect everything?
If it was simple life, I mean, the way I would think about it as a scientist is, first of all, if it was on Mars, my immediate question would be, is it separate to us? Is it our kin? But let's say we did we brought it back in a lab, we cut it open, whatever it was, we DNA dissected it, and we could tell for sure that it was completely separate from us. It was truly alien, not just a cousin. If it was truly alien, then you've got two planets in the same solar system next door to each other, which both started life. I think that, to me, implies that life is everywhere at this point. So all stars, all planets at the right distance for this, even remotely, because Mars isn't even really at the right distance, but even in the ballpark of the right distance will have life on them. So that's pretty profound. It would be a headache in some respects, because now if life is everywhere, all across the galaxy, there's 100 billion stars just in our galaxy. And yet we do not see any clear evidence for technological structures across these stars. We don't see spaceships flying between the stars. We don't see warp drives. We don't see stars which have been transformed into machines or engines. We don't see the supermassive black hole being tapped for energy. There's lots of things you can think about an advanced civilization might do once they get super, super advanced. We don't see any of that. And we don't really hear any radio signatures or laser pulses or anything. As far as we can tell, everything about our galaxy is consistent with there being just us in it. So then we call this the Fermi Paradox, becomes exacerbated. If every planet starts out with life, and that's in the right distance for life, and yet we're the only ones here, what gives? Like, that means there must be some incredible bottleneck, of order of like 100 billion bottleneck. So where is that bottleneck? Is the bottleneck behind us? Was it the evolution of the hominid? Of apes? Was that like, having something that had opposable thumbs and a brain? That combination is what you need for a technological species, and that just very, very rarely happens elsewhere. Because we had the dinosaurs, own the Earth for tens of millions of years, and they never apparently developed technology. So there's been advanced life on this planet that never got to that point.
Yeah, if there were dinosaurs on another planet, you wouldn't be able to detect that.
We could probably detect, the gases of them, like the oxygen, stuff like that. But we wouldn't see any cities, obviously, or anything like that. There's signs of we wouldn't see any radio beacons. But I think even with present technology, we couldn't even detect the presence of dinosaurs on a nearby exoplanet. No, that's just still beyond our capabilities. But the new observatory HWO could probably just about do that. And then the other possibility is that this bottleneck, sometimes called the Great Filter, is ahead of us. Maybe getting to this stage of technology is actually quite common. This happens par for the course. Lots of planets get to this point, but we are on the cusp of our annihilation in some way.
I guess there's annihilation, there's maybe disease, there's potentially asteroid impact, or maybe solar flares from the sun. There's actually all these dangers coming from every direction in different forms.
Yeah, I think the idea of an external threat to me, like an asteroid or a solar flare or something, is less threatening because A, we sort of know the rates of those happening, and B, we know the Earth has been hit in the past. I mean, the dinosaurs were knocked off, but it doesn't really matter. Life recovered, right? It wasn't the end of life on Earth when we got smashed by the KT transition meteor. Life recovered. Mammals were still around. Like they were burrowing down underneath the ground, and they just came out once things settled down and took over the Earth. So it was actually, some argue, that the impact of meteors is a good thing for the evolution of intelligence, because otherwise, if that hadn't have happened, dinosaurs would have ruled forever and never developed big brains.
We probably wouldn't have been around.
Yeah, you kind of need like a reset. Maybe sometimes evolution gets stuck in a rut and you kind of need to like kickstart things again, do a reset. Yeah, it's true of our own lives sometimes, right? You need to like do a personal reset and figure out where things are. So maybe evolution needs that same thing. So I'm not as worried about that. I think the more concerning feature is just the rate of acceleration in our own capabilities, not just nuclear weapons, but also the impact of how social media is making us a more polarized society, whether that's going to lead to more tribalism, more hostility between people, our capability to develop AI, nanotechnology, viruses, all of that are obvious reasons to be concerned that the more technologically advanced we get, the more capable we are of engineering our own death.
Yeah. Yeah, it's so easy to just, either if we go to war, create these incredibly powerful bombs, or even come up with some sort of a disease that just leaks and then takes over.
Yeah.
Which is why it's weird, because at this point now, relatively speaking, it's quite peaceful. As in, like, we're not battling any kind of disease or massive threat at the moment. So I always think, like, why? I think Elon Musk said this. Why don't we use our resources right now, whilst we can, to try and get off this planet?
Yeah, exactly. When you're in a surplus, you should invest that money.
Yeah.
Right? You don't just keep taking out more and more loans and spending it all. You want to like invest for the future of your returns. Sure, when you're in debt, then it's time to like put everything on keeping things going. But we are in a society which has lots of excesses still. I mean, we all know that. We have lots of excesses. So there's no reason why we shouldn't be able to do this. And so I'm totally on board with what Elon Musk says about that. There is a disturbing calculation that was done in the early 90s called the doomsday argument. And the doomsday argument is a statistical argument that kind of says that the end is actually quite close. And this technique was used during World War II it's called the German tank problem, by the Allies to calculate how many tanks the Germans were going to produce. So if you're an English factory trying to figure out how many tanks you need to produce, you don't want to produce 10 times more tanks than the Germans have, because that's wasteful. But you also don't want to produce 10 times fewer tanks than the Germans have, because that's not going to be enough to fight the war. You want to have just a little bit more. And so how do they know? So they captured a few German tanks and they had numbers on them. And so they looked at those numbers and it would say like, 3172 or something. And they'd be like, okay, this is 3172. So that's telling us they've made about 3,000 tanks so far. So reasonably, there's probably of order of maybe 6,000 tanks altogether. They kind of use this principle of mediocrity. It's probably this tank is probably not a special tank. It's probably not one of the very first ones they've made. It's probably not one of the very last ones they've made. It's probably somewhere in the middle. They used that argument and to calculate how many tanks they needed to produce, and it was right. They got it very close. The same argument was used by this statistician, Richard Gott, to predict the fall of the Berlin Wall. So when he visited the Berlin Wall, and when it was still up with a friend, I think it was in the 70s he visited or something, his friend asked him, how long do you think this will last for? And he said, well, okay, it's been stood for this many years, and I'm probably not going to be one of the first people that's ever seen the wall. I'm not probably the last people that's ever seen the wall. I'm probably somewhere in the middle of the timeline of all people that have witnessed this wall. And he used that to calculate a date for when he thought it would fall, and he was right to within a few years as well. So this argument is kind of eerily powerful. And if you use the same argument for human beings, there's been about 100 billion human beings that have ever lived on this planet. There's about 9 billion of us or 8 billion of us right now on the planet, right? There's a huge number of humans alive right now. The population was much, much smaller in the past. If you add up all of those humans, it's about roughly 100 billion. And so you might argue that we're probably not going to be one of the very first humans to have ever lived in the history of the universe, and we're probably not the very last humans to ever live. We're probably somewhere in the middle by the principle of mediocrity. And so that would predict another 100 billion to go. But because there's about 10 billion per generation, that means there's not very long left, in fact, in a time sense. And so he makes a prediction that sort of an order of a century, this is sort of the timescale we have left for humanity. And I guess the disturbing part of that bothers me is it makes sense in terms of like if you ever watch like The Foundation or Dune or something like this, they have humans everywhere, right? The humans are living on all planets across the entire universe because there's no aliens. So we just spread out and we just conquer the entire galaxy. In that universe, there would be trillions of humans. And they would look back at this time and they would think that was a crazy, unusual time, right? We now would live at the very, very, very beginning of all human history where there was just one planet. And, we didn't have all of this technology. We didn't have teleporters, we didn't have warp drive, what it would have been like to have lived in that time. And so, that puts me in a pessimistic view a little bit about this galactic empire vision, which I would love to be true. I'd love humanity to spread to the stars and become that. But it would mean I was a very exceptional human being if that was true. So I hope it's true. I hope there's something wrong with this argument we haven't quite figured out yet. But it's one of those things that worries me a little bit, along with all of these threats, of course, that we know about in our society.
The weird thing is, I feel like people just aren't really thinking about it. Like, it's not of their concern. Like, most of the people who are on this planet, they're just so self-absorbed with their life and just the day-to-day goings-on of what is happening in their life, not the broader spectrum of things. Like, where do we come from? Ancient civilizations, should we probably try and, ensure that we have a good chance of surviving? Okay, if that's the case, how do we do that?
Yeah.
I mean, even I was looking at the budget of NASA versus the budget of the military spending.
It's tiny, yeah.
And it's I think
it's about a quarter of the entire spending.
2023, the NASA budget was $25.4 billion, while the defense budget was $857.9 billion.
Yeah. It's a 0.25% of GDP. So it's, I think when you do polls, most people in America estimate it would be of order of 7-10%, something like this. And it's way smaller. So I think it just goes to show you how cost effective NASA is. It has such a huge impact. But you're to come at this point, like, people don't think about it too much about the future. And so there are some projects like the Seed Vault. Where's that in Scandinavia somewhere, where they've like stuck all the seeds of the earth into this vault just in case things go wrong. So we've got a backup supply. And there are preppers. There are some people which worry a lot about doomsday scenarios and think about that a lot. But as a society, we tend not to. We don't, and you think about like the national debt in every country pretty much in the world has the same problem, where we're all running huge debts because it's all about presentism. It's just about, getting now. I want everything right now, and I don't want to have to wait 20, 30 years, 40 years to bite the bullet, to sacrifice my current state of living to make the world and the future a better place. We seem to be so focused on our current state of affairs. And I do wonder whether this is somewhat inevitable for anyone who gets to our point, right? Because we live in a capitalist society, and it has, both with technology and science, it has always been massively bolstered by brilliant individuals. There's I don't want to downplay the impact of having large collaborations and teams, but individuals have certainly had a huge impact. I mean, Elon Musk is having a massive impact as an individual in space travel right now. Think about the impact of Einstein or Newton, these giants of the field, which just moved the needle forward so far. And I think humanity has always been advantaged by that. And so as a society, we have a very individualistic focused society. It's all about my own rights, my, thinking about what's best for me. And that's not necessarily the best thing for society. To optimize for yourself isn't necessarily the best thing to optimize for the planet. But maybe if we always optimized, if we were always so focused on the ensemble, you would kind of water out, you dilute those sparks of genius, right? Maybe you wouldn't be able to have that, those brilliant entrepreneurs who can push through and use that individualism to advance society in profound ways. And it's a similar kind of thing with tribalism and competition. We're a very competitive people. We love to compete with each other, or even against ourselves. We love to compete with other nations in sports teams, and scientists compete with each other. We like to, prove that we've got more publications that have bigger impact, Nobel Prize, whatever it is. We like to, show off about our achievements. And that competition drives us to become better. It drives us to innovate more and more and more. That's where, during wars is when huge amounts of technological innovation occur. We developed radar in England during the Second World War, purely as a product really of that tension of competition with the Germans. And so I kind of wonder whether if you took that away, if you took away the competition, maybe you just wouldn't have a technological species to begin with. So maybe competition is always part and parcel of any technological species. And if that's true, it's also the seed of our own annihilation, right? Because if that competition goes uncontrolled, it leads to hostility, tribalism, polarization, conflict, and that could be our death knell. So it's curious to wonder, is there such a thing as a totally benevolent society out there where it's utopian, or would they just still be farming and that's as far as they go?
Yeah, because I think Elon Musk, I think he was asked the question, and he doesn't believe in a society where there is peace. There will always be conflict.
Yeah. It's part of human nature to some degree.
Yeah. We'll get back to the podcast in a second, but first of all, I want to say a massive shout out to Bionic. I have been using their supplements for the past 4 years. I never knew what supplements I needed to take. I'd always go into the pharmacy and buy a load of random bottles and end up popping pills all day, every day, not having a clue if I was consuming the vitamins which I should be consuming at all. But Bionic came to save the day. They are a tailor-made supplement company that will put together your own specific formula based on your activity, your gender. I have Bionic Pro, where I get the blood test done every 3 to 4 months, and based on that blood test, I get my own personalized formula. For those people who don't want to do a blood test or don't have access to that, then you can go with Bionic Go, where you just have to fill in a short questionnaire, and based on that questionnaire, you will get your tailored supplements with a surprisingly high degree of accuracy. So stop the guesswork, sign up to Bionic, and ensure that you remove those deficiencies and build up your immune system. What do you think if let's say, for example, NASA's spending is 1 trillion, they have a budget of 1 trillion.
Mm-hmm.
What does that look like? Like, what would they do?
Wow. Yeah, even doubling the budget, which would be an extra 25 billion, would be game changing. We could having boots on the ground on Mars within probably the next 10, 20 years. But if you're talking about throwing $1 trillion at it, that's just beyond anyone's wildest expectations in the field of science and technology. So it's hard to imagine, but I think you could easily be building giant structures in space at this point. You could be doing space mining. We know that there are some asteroids out there, near Earth objects, that contain more rare earth elements than the entire planet Earth. It's like platinum, for instance. I think there's this asteroid that contains more platinum than the entire Earth. So if we mined that, that could be, and obviously that's people mostly think of that for jewelry, but there's a huge number of rare earth elements which are critical for battery technology and for other solar technologies that we're developing as well. So I think the ability to space mine would advance. It would be that kind of dream of a limitless, unbounded society where we just have everything we want. And I think investing in science has always been the key to unlocking that world of opportunity, of new resources. The Earth only has so many resources, and we're tapping it pretty hard right now. And clearly, we're running into conflict with other nations that they want to hold on to their rare earth elements, and they don't want to share them anymore. So that's going to have economic impacts on the US, and I'm sure elsewhere. So I think
it seems so silly when you think about it like that.
Yeah,
just fighting.
It's just tribalism, though, isn't it? It's that same thing of individualism. Of, well, I want to look after myself first, and look after you second, and that's just, unfortunately, human nature. We don't think of each other as brother and sister. We think of each other as competitors. A lot of people say if we ever detect an alien civilization, it would shift that mindset completely, right? And then we'd be like, okay, they're the other now. Now we can all work together to focus on the other, but somehow we always need the other. And then within that group we can collaborate, but we can't just be one unified group for the sake of it.
I think Arrival, that was a great film where it depicted that, where we're all competing against each other because we didn't want to share information. And then eventually all the nations got together, they shared the information, and they unlocked this code and formula, which was like the key to progressing life even further.
Yeah. I mean, how society would change. Some people say like society would just get on. Like you'd still get up the next day and go to your job, and in a day-to-day sense, maybe nothing would really change. But I think it would proliferate into our philosophies and outlook of life, that the universe is not the same anymore. When you discover someone else, you now know that there's more than this just pale blue dot of light. There is a whole universe of potential civilizations out there who are waiting to interact with us and engage with us, and we'd probably take a lot more responsibility and try and mature as a civilization, I think, at that point, right? You don't want to be embarrassed by they're looking at us saying, wait, you're still burning all those fossils from the ground. Like, you do realize you're poisoning your atmosphere. But okay, actually, we'll stop that now. We'll stop. Like, it would probably help us to figure things out a little bit. Yeah. But I have to be candid and say, I'm not optimistic I'm going to see that. I'm not optimistic I'll see the day of a advanced civilization being announced in my lifetime.
You are optimistic.
I'm not optimistic. I think
I am.
Simple life, maybe. I mean, I hope.
I think there's stuff under the pyramids and under the Sphinx
that is alien,
hidden. That because Hawass. There's a lot of gatekeepers in Egypt who are preventing archaeologists just doing their thing. And great YouTube channel, Uncharted X. The guy goes into the description of what might be underneath not the pyramids, one of the pyramids. There's this huge labyrinth, which is this underground structure which is said to be greater than the pyramids themselves, but we just can't
access it.
So I think there will be, I'm hoping, and this is the thing, I'm probably hoping more than anything else, that there will be some sort of discovery made which will prove that there was an existence of a previous civilization that was technologically advanced, that had the capability of doing things that
would they be alien in your mind, or would they be another Earth-based civilization? Yeah. So that idea is, I mean, there's scientific grounding for that for sure. There's an idea called the Silurian hypothesis that suggests that there could have been a past civilization that was pretty advanced and we wouldn't know about it over geological timescales, hundreds of tens of millions.
Everything
of years.
Breaks down eventually after, if you're looking at like hundreds of thousands of years.
Yeah,
things decompose apart from the metals themselves.
Yes, I mean, you could have another ancient Rome, ancient Greece that was 10 million years ago, and we'd have no trace of it now. It'd just be lost in the eroded away completely at this point. I think it's harder to imagine a civilization that had as much plastic and as concrete as we've made, right? So those are, if you talk to anthropologists and geologists, they are currently trying to encourage us to classify the current geological era as the Anthropocene. Anthropo means like humanity. So there's, like the Paleocene, there's the Holocene, and we want to create a new category, which is the Anthropocene, which is essentially the effective technology of humanity. And that's, if you went 1 billion years into the future, and these...
Oh, there'd be like a layer.
Yeah, exactly. You look in the rock layer, you would see plastic.
pure pollution.
Yeah, you'd see radioactive elements, plastic, you'd see concrete, you'd see even chicken. Like they were pointing out that chicken carcasses you'd see sites with just like 1 billion dead chicken carcasses in one place, which would make no sense.
Yeah.
Why is there so many chickens that died in this one place? So it would be really profound impact in the geological record. So I think we're fairly confident there was never a civilization which got as far as we are. There's nothing on the moon, right? The moon is totally pristine. There's no weather or erosion on the moon really of any kind. Neil Armstrong's footprints will be there for another 1 million years, and the Apollo landers will be there probably forever. I don't think there's any way those would erode unless you go into like trillions of years into the future. So there's no other Apollo landers on the moon. Right? We've imaged every damn centimeter squared of the moon with, unless there's a conspiracy or something.
Why is there so many conspiracy theories about the moon?
Yeah.
If you just type in moon conspiracy theory on YouTube, there's so many videos. Then people claim that the moon is hollow.
Yeah. Or made of cheese or whatever it is. Yeah. And a while back there was this lunar hut that I remember reading about. So there was this Chinese lander, a rover that was driving around, and there was this photo of this thing that looked like a little hut in the background is like perfectly square lunar hut. And the Chinese media called it that in their press release. They called it like mystery hut. And so when the Western media got hold of it, they were like, what the hell? The Chinese have discovered like an artificial structure on the moon. And so they redirected the rover to drive over and get a closer look. And when it got a closer look, it was just like it was just a normal rock. They're just in the blurriness, because it was so far away when it took the photo, you couldn't really figure out what it was. And that's true so often, that things that look really compelling are just on that, we sometimes call it the low information zone. Like the things which are just blurry enough that they're intriguing, but you don't have high quality, high resolution images of. And so often, these, whatever it is, be it, things under the pyramids or lunar hut or face on Mars or UFOs, often this stuff is at that ambiguity regime where you can inject your own hope.
Imagination.
Really hope that could be the real thing. And those hopes have often, in the past, taken us down the wrong path, unfortunately.
Guess the views. That's
yeah, right. I mean, if you go back a century and a half ago, there was this dude, Percival Lowell, an astronomer, who was arguing that there was canal systems on Mars, right? And so he was seeing these lines on Mars with the early telescopes, and he was on the front of the New York Times with this article saying there's a canal civilization on Mars, and it was all in that low information zone of it just being blurry enough that you couldn't quite tell what it was. And he injected his own hopes, like he really hoped there was a civilization there. So I think that's where you have to be so cautious, not just in science, but in a guide for life, is really ask yourself, what do I want to be true? Maybe it's like a news story you're reading about a political person you don't like, or a celebrity you don't like, whatever it is. What do I hope to be true in this case?
Yeah.
And then just kind of like really be cautious about it and think, well, whatever I want to be true, I need to almost act the opposite direction consciously and fight against it, because my brain is very tempted to trick me here. And we've seen that so many times. I've seen that personally as a scientist. I've had cases where I thought I detected something that would change my life. And, I was imagining all these prizes and accolades if this was true. And then whenever you hit that moment of like, this could be it, this could be my big break, obviously keep pushing, keep trying to get to that next step. But also just take a sober beat and think, am I deluding myself here because I want this to be true? And sometimes you need that.
I would imagine there's a lot of scientists and astrophysicists out there who they're just so stubborn in thinking that their theory is right, or hoping that what they believe is to be right, that they refuse to listen to other points of views.
You're absolutely right. I mean, there's sometimes that physics advances one funeral at a time.
Yeah.
So it's only when the old guys die that ideas can move forward. And I mean, that was true. That's been true throughout science. But, it's often the young people who are coming into the field who are uninitiated and unstained by paradigm, right? So they can think outside the box because they don't have any bounds on them. Whereas someone who spent 50 years pushing a particular theory, they're locked in.
Yeah.
And it's really sad. There was one of the first ever planets that was announced, an exoplanet, was all the way back in 1969 by a Dutch astronomer called Peter van der Kamp. And he claimed this star, Barnard's star nearby, had the first ever exoplanet. And he stuck to his guns even when people started to say, I'm not sure about this, the dynamics don't work out, there's some problems here. But he just kept sticking to it. And then he kept changing the mass of the planet. So he said, actually, I know initially I said it was 6 Jupiter masses, now it's 2 Jupiter masses, now it's half a Jupiter mass. So he kept, dialing it down. So it was always just below what we could see. And then eventually the Hubble Space Telescope pointed at it like 30 years after he made this prediction, and it didn't see anything, and it totally ruled out this planet being there. And even on his deathbed, he still insisted that everyone else was wrong, the whole world was wrong, and that planet was there. He could not let it go. And I think that's really sad when a scientist gets so married to their theory, to their ideology, they can't move. And we all do it. We're all humans. Everyone gets married to an ideology.
Especially imagine if you dedicated your whole life to this one particular point of view.
Right.
And you find out
you
might actually be wrong.
Yeah, it's always weird to me when someone says, I'm a proud Labour voter my whole life or something. I'd never vote for another party or Republican or whatever it is. And you just think, well, so no matter what happens, you're never going to change your mind. That just seems like the opposite of you activating your brain. Like, you just think about what's happening and make a judgment. And so it is sad when scientists of all people fall in that. And it is, it's sometimes said that science is supposed to be a place where anyone with a single piece of evidence can prove someone else is wrong. In practice, it's harder than it seems. If you're a young person and you have a great idea and you want to prove that Einstein is wrong or whatever, you have to overcome the entire institution of academia, right? There's going to be hundreds of thousands of scientists that just think you're an idiot for even saying that and won't even entertain what you're coming up with. So we have to be careful about groupthink, of being so locked in to paradigms that we're no longer willing to listen to innovative new ideas. But then on the other side of it, my inbox is full of crazy ideas all the time. I get so many emails from people saying, I've proven that God exists. Here's
my formula.
Some formula. I get hundreds and hundreds of emails like this, and I don't have time, frankly, to review them all. Right? It's just too much coming into my inbox, and lots of scientists, it's the same thing. So we all have to prioritize our time a little bit, and you're always making that judgment of, do I investigate every single thread of crazy or what appears crazy?
Because there probably will be quite.
But one of them's probably right. Out of these hundreds, thousands of lottery tickets, someone's probably going to have a genuinely really good idea, and I'm probably going to miss it because there's just so much noise flying my way, and it's true of so many of us.
Well, I guess the good thing about today's day and age is, if no one's going to listen to you, then at least you could just get a camera and just start filming videos, and then maybe someone somewhere will eventually catch on and be like, oh, this guy's onto something. Yeah.
Certainly the democratization of science is improving with social media.
Have you got ridiculed for anything? You came up with the concept of the Halo drive.
Yeah, the Halo drive.
As you do.
Yeah, I didn't get ridiculed for that. Well, you know what? I did get ridiculed. Maybe we could talk about that in a moment. But I did get ridiculed early on in my career for looking. One of my things I'm most well known for is looking for moons around planets. And so I remember when I first arrived at Harvard University, when I was probably like 22 years old or something, 23, I was so excited to be there, and I was terrified by all the names on the doors walking down the corridor, these like giants of the field, Dave Charbonneau, Dimitar Sasla, people who in my mind were like the heroes, in my field. And I remember walking down this corridor, and there was a coffee hour around the corner every morning, and I guess there was some gossip that I was the new guy who'd arrived. And they knew that I worked on moons, and to them it was ridiculous because we'd only recently started finding planets. So the idea of looking for moons was like pie in the sky stuff to them. And so I remember hearing them joke about it, saying, oh, is the moon guy going to turn up and talk about these crazy ideas for finding exoplanets? And I remember I walked around the corner, and they all just kind of went quiet. And,
hey, guys.
Yeah, it's like a really awkward first coffee. So I was kind of not ridiculed to my face, but I know there was people who thought what I was doing was crazy. But I knew it was to me, it just didn't make any sense what they were saying. Like, we know planets in the solar system have moons. Like, there's hundreds of moons in the solar system. Of course, exoplanets must have moons. And why would we assume they're all as small as the moons in our own solar system? Some of them could be quite big and thus detectable right now if we're lucky. We should try. We should do the experiment. We should look. So that was always my opinion.
Nobody was really doing this.
No, I mean, at the time it was just like Wild West stuff to be looking. It sounds crazy like now because it's actually become quite mainstream to look for moons. But at the time it was Wild West stuff. And so is, back then, like the giggle factor, as we sometimes call it, was applied to looking for life in the universe as well. People thought that was just like, oh, you put your tinfoil hat on, or you've been watching too much Ancient Aliens or whatever. Like it was even that still today has a bit of an edge to it. And yeah, I think it's a shame when we start ridiculing colleagues like this. I think it does a disservice to open scientific debate because then it kind of shuts down conversation, right? It's whenever you kind of bully someone through emotional means rather than just trying to address the scientific validity of their argument, that's when you've lost. Whenever someone starts invoking ad hominems, that, like anyone who doesn't agree with me is an arrogant prick or something like that, I immediately think, okay, well, you've lost the argument, right? Because you're now having to fall back to this kind of Graham's pyramid of argumentation, and at the lowest level is ad hominem, and the next level is like whataboutism, like you just deflect to something completely different, which politicians do all the time. And so I'm always very conscious of that, and I just want to talk about the argument. Like if with 3i Atlas, we talked about this interstellar object, Avi Loeb has come under a lot of heat for saying this could be an alien spacecraft, and I think the evidence is pretty clear at this point. This is not an alien spacecraft, but I think we shouldn't ridicule him for suggesting this as a hypothesis to explore. It's an interesting hypothesis. We could think of experiments to test it. And there might well be stuff flying through the solar system which is alien. How do we know? Why are we assuming that's crazy? We haven't done the experiment. We don't know. So I don't like it when we ridicule anyone in my field for making legitimate scientific arguments.
And the A3 Atlas, that's what it's called?
3i Atlas.
3i Atlas. Why is he thinking that it's potentially alien? Just because of the speed that it's traveling at?
The argument seems to be evolving a little bit, which is one reason to maybe be skeptical about it. But the initial argument was the speed of it was very fast. The trajectory was unusual. It kind of flies very close to the plane of the solar system, and it's making a pretty close flyby to Mars in October, I think, next month. It's on the way in still. It won't come anywhere near the Earth. So this is for me one reason why I'm like, if it's an alien spaceship that's making a close approach to Mars, it seems much more interested in Mars than it does in Earth, right? So that's already kind of strange. And he calculated like the probability of it going so close to, Mars, Venus, and Jupiter. And the probability of it going past each of them is something like 1% probability. And so if you multiply 1% by 1% by 1%, you get this like very small number. So he was like, okay, this is incredibly unlikely to happen by chance. This is a spacecraft. But I pointed back when I made a counter rebuttal to this that what if you chose Saturn, the Earth, and Mercury instead? Then the probability is like 50%. It's a bit arbitrary which ones you pick as to how you engineer these probabilities. So the trajectory, and then the third thing was the size of it. So early images of it, it was unclear whether it was a rock or a comet. If it's a rock, it's an asteroid. If it's a ball of ice, like a snowball, basically, it's a comet. And we couldn't really tell from the early images which one it was. If it was a rock, though, it would have been huge, because you could tell by the physical size of it, like it would have been like the size of 40 kilometers across or something. It would have been absolutely gigantic. And Avi Loeb made the argument that it's so big, there's no way it could be natural. Like if you do the calculation of how often something that big should be randomly flying around, it's just tiny, tiny, tiny chance. That's another reason why we should think this is a spacecraft of some kind. However, if it's a comet, then what you're seeing isn't all surface. The actual physical nucleus of the comet is buried right in the middle, and then it's got all this dust and like an envelope of atmosphere almost around it. So what you see is like the shroud of dust, and the true size is much, much smaller than what you think it is. So as the object has got closer and closer to the sun, we now see a cometary tail come off it. There's been these beautiful images by Gemini, a telescope, and the Hubble Space Telescope has captured it as well. James Webb has observed it. So we now know with great confidence it has a cometary tail. There are still weird things about it. It has a lot of nickel, for instance, coming off it. That's unusual. I think Abby has been suggesting, that could be part of some kind of factory or something, some industrial process happening on board. But he didn't know that when he first made the alien argument, to be clear. And it also has some weird amount of carbon dioxide versus water coming off it. So there was definitely like some weird things about it. I don't want to dismiss it as a totally ordinary comet, because that's not correct. But it is also only the second ever comet we have ever seen come from another star system.
Yeah.
So we don't really have much.
And we've only seen
precedent.
3 objects.
Yeah, maybe that's what they all look like.
Yeah.
As far as we know. We don't know. It could be that they all have nickel coming off them, as far as we know. We've only seen 2 of them, and the other one we didn't really study very closely. So I think it's perfectly possible that this is just a new type of comet. Why should it be that all solar systems have comets that are exactly the same as our comets? They have different chemistry. They're born in different environments. Some be closer to the galactic core. Some can be in, dense stellar nurseries. There's all sorts of weird stuff that could be going on out there.
The weird thing about that Oumuamua was that it didn't follow the predicted trajectory that it was supposed to follow. Once it went past the sun, it went off at a different angle or something.
Not quite. It had a slight amount of excess speed. It was accelerating. So it didn't like change direction, but it did move faster along that trajectory than it really should have done. And the mystery of, actually comets do this often. So as a comet goes past the sun, it warms up, and so stuff comes off it. And that actually acts like a jet. So it's like if you spit stuff out the back, like a water jet, you're going to propel yourself forward. So you accelerate a little bit forward. So at first, a lot of people just assumed it was that. A lot of astronomers thought, well, it must be just outgassing something. The weird thing was that then when we looked for those chemicals that were being outgassed, we couldn't see anything. So we went through a list. We had a list of, I can't remember the exact list, but it was things like carbon dioxide, ammonia, water, stuff like this. Went through this list. Do we see this? No. Do we see this? No. Do we see this? No. The typical stuff that comets emit. And it didn't seem to emit any of that stuff. But there were still a few molecules we didn't check. So the back door here of escape is to say it's just outgassing something we didn't check for. We didn't have time because it was moving out of the solar system before we had a chance to do those observations. I think still that's the most likely explanation. Otherwise, you have to say, yeah, it's a spaceship, which is just a big move to make, because that's a pretty, if that's the only solid ground you have for your evidence that it's moving slightly, and we're talking like millimeters per second squared. It's not like moving fast. This is not like going close to the speed of light out the solar system. It's like a 0.01% excess speed that it has. So to me, that's not enough. I would want to see it personally. I'd want really compelling evidence. I want to see it like change direction.
Yeah.
I want to see it zigzag around. I want to see it stop and do something, just stuff that like there's no way there's possibly an explanation as to how it could do this. But for Oumuamua, there's definitely still a back door to explain it naturally. And as long as you have a plausible back door, for me, that's not enough. You have to rule out everything. Once everything's ruled out, then I'd be happy to say, okay, the only thing left is aliens at this point. But
if we had enough warning, would we have the capability to put something out there to fly alongside it, or was that not possible?
Yeah, that'd be really cool. Oumuamua was moving quite slowly, so it's actually quite easy to intercept that one in principle. 3A Atlas is moving really fast, about 3 times faster, so it's harder to catch up with that guy. But it is possible. So, especially if you use existing spacecraft which are already in the solar system. So we have a few probes that are already in orbit of Mars, for instance. And during the Mars flyby, 3 Atlas is coming pretty close to Mars. You could turn on the jet, turn on the thrusters of one of those spacecraft and try and catch up with it. And it should just about be possible, I think, for one of those. But then you'd basically sacrifice the Mars mission that you've got. So the question is whether, I don't think the science teams who, they have their own science questions they're interested in about Mars, they're probably not willing to shred up their mission to do that.
Years of work, probably millions and billions.
Yeah, realistically, you need to think ahead. And so there's a European mission called the Comet Interceptor, which is being planned. I think it's 2030, roughly, they plan to launch that thing. And the idea is you basically park it in the solar system, waiting for the next thing. So it's just lurking there, waiting. And as soon as you see it, turns on the thrusters, catches up with that thing, gets some beautiful images, maybe land on it, maybe get a sample as well. So that would be the most obvious way to do that.
That's good. Let's say worst case scenario, one of those was heading for Earth. Do we have the ability to deflect it or blow it up?
Depends on how much warning we get. Comets are always, and interstellar objects as well, I suppose, are always a very serious threat in this regard. There's basically 2 types of objects which could annihilate the Earth, cause mayhem on the Earth. One is what we call a near-Earth object. So this is something which is basically orbiting the sun at the same distance that the Earth orbits the sun, more or less. And there's thousands of objects like that. Very small rocks, and they're not stable. Over millions of years, they get pushed into different orbits. They don't stay in the same place. But because of that instability, there's always a chance that they could move and strike the Earth. So there was a directive from Congress in the United States to track down over 90% of those. So we know where they all are. We know what the threats are. And we're more or less going to get to that point thanks to this new observatory that's just come online called Rubin that should be able to find pretty much all of those things, which would be great. However, a comet is a completely different story, because comets are not nearby the Earth. They're coming from the distant depths of the solar system, and they're really far out, and so we don't know about them until they're basically heading right at you. And then it's that last moment when you're like, oh shit. So you actually see the thing. It's kind of like a truck, when you're sleeping at the wheel and the truck just suddenly puts the lights on. That's the moment you have to catch it, when those headlights come on and the horn starts beeping. So there is a bit of a panic for a comet. So again, Rubin is going to extend the warning for that. So I think before, the warning was just like maybe a couple of days that we'd have for a killer comet.
A couple of days, really?
Yeah, and now it's more like a couple of months, maybe a year if we're lucky. So it's still not very long, but it's maybe plausible that we could get something off the ground. And I mean, we would, right? If it was that desperate, we'd figure out a way to do it. And then the question is, how do you deflect it? If it's a comet heading straight at us, again, you don't have much time. So normally with an object, if you have years or even decades to deflect it, there's lots of stuff you can do. You can just basically park a small spacecraft on the surface, turn on its thrusters, and it will just nudge it very slightly out of the way. And even a small nudge, if you're far enough away, is enough to save you. But if it's heading straight at you and it's big, and you only have a couple of weeks to play with, it's basically the nuclear option is all you've got. You're just going to have to try and blow that thing up. But realistically, the best strategy is not to detonate the entire comet, but to detonate just to the side of the comet and then again nudge it off. Because if you detonate the whole comet itself, you just get all these fragments which are still pretty much heading in the same direction. So you kind of want to like bang, push it off to the side and save yourself that way. But again, the more notice you have, the easier that is, because then the less nukes you have to use to do that. So
how big does it have to be for it to be like a substantial threat?
I think of order of like 100 meters across will destroy a city. But then it has to actually hit the city itself. About 1 kilometer would have global impacts wherever it hits. And 10 kilometers would be sort of the size that would be an extinction level event for some species on the Earth. Whether that would annihilate humanity is a open question, because humanity is, I think, a very resilient species. We're, covering the planet pole to pole. We even have humans in space. We have seed vaults. We have, preppers. We have people, there are a lot of people who are resilient, and I think humanity is a very resilient species. So I think we would be very difficult to completely knock off the Earth.
I'm sure there's a lot we don't know about the plans which the elites have. Governments have.
Some of these planets, they have these like basements that go down like 30 levels, right? And it's a complete biosphere almost underground that they can survive the rest of their lives down there. So, the interesting thought about that is that maybe humans are actually very difficult to get rid of on this planet. Think of ourselves as fragile. If that's true, maybe societies easy to collapse. I think, capitalism, the economy, modern society is probably fragile, but the actual biological species of humanity is probably more resilient than we give it credit to. And I think I could imagine one of these impacts or some disease or something, collapsing society down back to sort of caveman times, essentially. But humans would bounce back. It would maybe take another, 100,000 years for us to climb back up that ladder again. But I think we'd be hard to totally scrub off the surface. I think we're almost like an infection of the planet at this point, right? It's hard to completely scrub us away. And that gives me hope that, even if this experiment, this iteration of humanity ends, there will probably be other iterations down the future, which is interesting for your, speculation about the pyramids and stuff. Yeah, it's not unreasonable that civilizations could collapse. They do collapse and then go through a reset and then eventually come back again in the future.
Do you think Mars can be colonized? And on another question about that is, is it better to colonize a planet or a moon?
I think Mars makes the most sense for a settlement or a colony at this point, because it has many of the resources that you would need. The moon is the next obvious place to consider. The moon is very dry. There's not a lot of water there. There is some at the poles, and water is critical for our survival, not just for hydration, but also you can split H2O to make oxygen, and you can use the hydrogen then for rocket fuel. So it's sort of the basis of a Mars base or a moon base. Mars is much wetter. It has a stronger gravity. It's unclear what the effects on the human body would be living in such a low gravity environment as the moon for a long time. We know that astronauts who are in microgravity in the International Space Station have huge physiological problems.
They lose a lot of their muscle.
They lose their muscles. Their eyesight gets hugely impacted. They get kidney stones, right? Because your muscles are not only degrading, but your bones are degrading. That calcium then gets processed into your blood, into your kidneys, and forms stones. So yeah, everything, and of course you're being exposed to high radiation, which is probably going to shorten your ultimate lifespan due to cancer. So there's many health detriments of being certainly in orbit of the Earth. And if you were on Mars, there's some benefit by having a stronger gravity. I think the gravity is about was it like about 20% the Earth's gravity, whereas on Mars it's about a sixth. So it'd be, I think, having a stronger gravity, maybe a stronger, there's a very weak magnetic field around Mars as well. We can think of ways to maybe strengthen that. So there are certainly advantages to Mars, but the thing with Mars is, who wants to live in Antarctica, right? Antarctica is a brutal, hellish environment to live in. And even the most adventurous humans rarely spend their entire lives there. They might live there for 6 months and they're like, okay, I've had enough of Antarctica. That's enough for me. But if you went to Mars, it'd be worse than Antarctica and it'd be for the rest of your life, right? It's pretty much a one-way trip. So it's a pretty brutal environment, and it's unclear to me whether we have the technology to live there today, but I certainly think it's within the realms of possibility. We can think that all the problems we can think of solutions to. We maybe don't have the solutions fully developed and fleshed out yet, but there's no showstopper to us living on Mars. So I think eventually it probably will happen, and it probably should happen. It'll be a benefit because it will protect us to some degree.
I just wouldn't want to be the first person to do it.
No, I don't think I even want to visit Mars, to be honest. It's because it's also a really long way. It would take you about 9 months to fly there, and you're exposing your body. I mean, you'd lose all your muscle mass. Your eyesight, as I said, would go downhill. You basically take like maybe 5-10 years off your lifespan, your health span. So there's no. To me, this is not obvious to look at a desert when you get there at the other end. It's going to be that worth it. The moon, I'd be interested in going, because that's only like a 2 or 3 day ride. It'd be kind of fun to play golf on the moon or something.
Yeah.
So
I reckon they'll probably turn that into a tourist hotspot eventually.
Yeah, I would love to go and see, where Neil Armstrong's footprints were, right? And see the Apollo landers. That should be like a national heritage site almost, or a lunar heritage site. It'd be really fun to visit there.
Mm. Is there any films that have come out that you feel as though have actually got it like right?
Yeah, I mean, The Expanse does a pretty good job, that TV show. The book series is really good. I think a lot of astronomers point to that as one of the closest to hard science fiction in recent years, because they think really, they don't have warp drives, they don't have, or at least they do kind of eventually have something that goes faster than light, but that's an alien technology which does that. But all the human technology is kind of within the bounds of what we're imagining. They have this kind of cool concept where they hollow out asteroids and they live on the inside and they spin them. So if you spin an asteroid, then you get the centrifugal force, like when you bank a corner in your car, you get pushed to the side. And so that can create artificial gravity. So that's an idea that astronomers and physicists have been talking about for decades. And so it was really fully fleshed out in the show and in the books. And that would be like a really obvious way to sort of overcome some of these problems of low gravity, for instance. So I think that does a pretty good job. This film's like, I personally love Interstellar. It's always been one of my absolute favorite films of all time.
Yeah.
But some of the science goes a little bit wonky, especially towards the end of the film. But I give that a pass.
Going in the black hole.
Yeah. But, well, you could probably survive going into the black hole. How the hell he gets out of the black hole is
But I thought if you were going into the black hole, you'd just get so stretched that you would die.
This is actually where the film does a good job. So normally you would for any normal sized black hole, but weirdly for a supermassive black hole, you can actually survive. So the event horizon is this kind of critical distance where once you pass the event horizon, even light itself can't escape from a black hole. And so the question is how strong are what we call the tidal forces, that's the stretching forces, at that point. And it turns out that the tidal forces around a small black hole at the event horizon are brutal. They would savagely rip you apart. Whereas the bigger and bigger you make the black hole, the event horizon rapidly moves out. And so it moves out far enough that actually, as you pass the event horizon for the black holes in the center of our own galaxy, it probably wouldn't kill you. You probably wouldn't even actually notice anything, to be honest, as you pass the event horizon. So a human could enter past the event horizon, which is what obviously happens in the film. You would never get out, of course, as far as we know. That should be possible to get out. But it'd be, I've always wondered, like, if that was a possible option, like if you knew you were going to die and you had, like, you were terminally ill or something, and you were given the option, hey, if you want, you can just throw yourself into this black hole. Would you want to see what's on the other side?
Yeah, I'd do that.
Right? It'd be kind of fun. Like, if you know that's it, this is a question that it's a weird question because only you could ever know the answer. You go in and you can never tell anybody what you saw, but you would scratch that itch of knowing is what's at the bottom of the black hole. But eventually,
parallel universe or another universe or nothing at all. Yeah.
I mean, eventually though, you would probably get totally ripped. So even though you survive passing the event horizon, you're still falling, and so you still will eventually get closer and closer towards the singularity and be ripped apart at some point. So there's no way of escaping spaghettification. It's just whether it happens at the threshold or not.
Yeah. Are you friends with Brian Cox?
I wish. He's a cool guy. Yeah. No, I've
not
never.
At the point where you can share thoughts.
I wish, I've never interacted with the dude. I love his work though. Yeah. I've interacted a lot with Neil because I'm in America, so I'm in New York. So Neil is in the same city as me, and so we chat a lot. I've been on Star Talk a few times. So I guess as a product of being in the US, I'm a bit more plugged into the US SciComm network than I am in the UK. But hey, I'm here for a year now, part of my sabbatical. So I'd really love if Brian listens to this, let's chat, because I would love.
Because he's someone I would love to speak to as well, because I think what the world needs more of is people like you guys who are incredibly knowledgeable, but you have this ability to communicate very well and break down complex topics, and it's just easy to listen to. You know, because there's certain people who are just so smart, but they're impossible to listen to. Either they're just bad at communicating, or they're speaking in a different language, as in, like, it's too complex. Like the average person cannot fathom or digest what it is they're saying. Yeah. But you guys do a great job of breaking it down for the slower people like me.
That's very kind of you to say. I think those people are actually too smart for their own good. It's like I think the advantage of maybe why I think I'm a good science communicator is because I'm not so smart. I'm not a genius. So for me to get my head around stuff, I have to break it down into simple steps in my own head. Yeah. And then once I've got a simple step formula as to how I understand it, I more or less just share that online. Yeah. That's my recipe. And I think the people who are just these super brilliant geniuses, it's all so natural to them, they don't even think about
like, how do
what the recipe was to get.
Not understand that?
Yeah. It's just too inherent to them. So I think somehow being a little bit below that level is useful as a science communicator. Yeah,
we're doing a good job with the YouTube channel. It's very good.
I know, it's amazing. I started that channel with no intentions of it becoming a big thing. I did this, I think when I started, it was about 10 years ago. And there was not a lot of scientists doing science communication at the time. It was, you can find science videos for a long time. One of my favorite channels of all time was Vsauce. Love Vsauce's videos. I've always loved those. But that's a individual who is not a practicing research scientist. And so when I created the channel, I was like, hey, what if we actually have someone who's in the trenches telling you what it's like, rather than someone who's seeing it from the outside? Someone who's actually in the game, it's got some skin in the game. And so that was my motivation. It was pretty unusual at the time, but now there's a whole bunch of us doing this kind of stuff, and it's quite refreshing. And I think it gives a whole level of authenticity to it. And I think that's a new generation. That's a YouTube thing. That's not maybe of the same ilk of like Brian Cox and Neil deGrasse Tyson, who grew up more like, they're very focused on a total science communication model. Whereas I spend much more of my time doing research than I do doing science communication. So this is always like the side project stuff for me. And it's weird because it's very lucrative doing science communication once you get to this level. And so I would certainly make more money if I just did this, but my passion and my love has always been research, and I don't think I could be, science communication is a bit like being in love. You just want to tell the world about it when you're in love. You can't help talking about this, how wonderful your partner is, or, how great yesterday was hanging out with them, whatever it is. But at the same time, you don't want to stop hanging out with them. You want your whole time just to be talking about being in love. You actually want to spend a lot of your time with that person. And so for me, those are the two sides of the coin. And so I can never imagine going full gung-ho in science communication, but
because if you're speaking or doing a podcast or making a video, you kind of like, man, I just want to get back into the paperwork and doing the research.
Well, you get ideas as you're doing it. You're thinking, oh, that's a good question. Actually, I don't know the answers to that. We should look into that. We should start a paper about that. So, but that's another great side of doing SciComm. If you don't do any science communication at all, if you're just a pure scientist, you do get very stuck in that lane and very niche, right? You kind of like, what's the next ultra niche question about this thing that I'm working on? And so for me, it was exomoons, right? And so if I hadn't done science communication, I'd probably just be doing more and more exomoon moons and rings of moon, like very, very subtle, distinct stuff. But as a product of being a science communicator, I've been pushed more and more into the mainstream questions that people really care about. I'm very in touch, I think, with the things that people really are interested in, because I speak to folks like you and other folks who ask me these great questions, and then that affects me. I'm like, yeah, these are the things people really care about. Like, I should probably balance my portfolio to get to the nitty-gritty of the big questions rather than just going too deep into these subtle issues. So I think it makes
you're trying to balance it between what you're really interested in, but also what the public is interested in.
A little bit, yeah. And also, I mean, like the halo drive we talked about earlier, to come back to that, this is this interstellar propulsion system idea that I came up with. So if you had a black hole, you could do a gravitational slingshot around it, right? You could swing around it and you could actually steal speed from the black hole to go really, really fast, close to the speed of light potentially. And so the danger of that, as we talked about earlier, is a spaghettification. If it's a small black hole, which most of them are, you're going to get ripped apart by doing this maneuver. So my insight was, hey, maybe we could use a laser beam. You could actually shine a laser. It will boomerang around, because light bends around black holes. It'll boomerang around, come back to your spaceship, and light carries momentum. So it'll actually push your spaceship forward. So it's kind of a way of doing these slingshots remotely. Like, you don't even have to fly that particularly close to the black hole. You can steal energy from them from a great distance, and avoid that hazardous environment. Now, that is a wild idea. And what on earth is someone who studies exomoons got any right thinking about that? And it's because I'm doing science communication that folks are asking me and engaged. I can see there's a huge appetite for interstellar propulsion. So I'm making videos about it. And as I'm making videos about it, I'm thinking, hey, what about this? How come no one's done this before? I should write a paper about this. So,
well, if we unlock that, then that opens up the entire Milky Way, if we can find a way of actually transporting quickly.
Right. I mean, I will say the beauty of the halo drive, it has obviously a big disadvantage that you have to have a black hole first. You have to get to a black hole.
We have to figure out how to, get to it or make your own.
Or you could make your own potentially, yeah. But the great advantage of it, certainly with natural black holes, is that there's really no mass limit. You could accelerate entire Jupiter-sized planets to close to the speed of light using them, because the black hole is so massive, it doesn't really matter. So unlike most propulsion systems we think of, we're always concerned about the weight, like make it as light as possible so you can go as fast as possible. The halo drive doesn't give a crap about that. You can make this thing as heavy as you like. So if you wanted to move an entire civilization, this would be the way to do it. And there's probably of order of 1 million black holes in the Milky Way. That's a lot. And they're spread about fairly evenly across the disk of the Milky Way. And so to me, they form like a nodal highway system, right? So if you would accelerate between these points, and you can use them to both accelerate and decelerate. You can slow down as well. You can brake. So to me, this is kind of your highway system. And then once you get to your destination, you off ramp, and then you use your more conventional methods to go to the star that you actually care about. So that would be my vision. And I think, an inspiration from that is, hey, maybe we should pay more attention to black holes as a place where aliens might be hanging out, because they have so many advantages in that respect.
Amazing. What do you want to be known for like all the work that you're doing?
Yeah, I don't think about legacy too much. Maybe I should. I'm 40 years old now, so I probably should start thinking more about legacy.
I imagine you're hoping to get more people interested in the topic.
Yeah,
Help
I
to
mean,
understand.
when I do science communication, like I said, there isn't a super clear objective goal besides from like that analogy of being in love, of just wanting to talk about it because it's ingrained within me that I just love this topic so much. I want to share it. And I get frustrated sometimes because when I'm at home, my wife's heard all about space so much. She doesn't want to talk to me about space anymore. Just like, I've had enough of that. Let's talk about something else.
On to the kids next.
But sometimes it's really fun. Yeah. When like visitors come over and they're like, "Oh, you're an astronomer." And I'll just sit them down and I'll just like, okay, it's fresh meat. And I just love like sharing this passion I have with people who are engaged with it. So it's always like a great pleasure for me. It's like an outlet rather than something with a strong, here's the objective function that I'm trying to optimize for. And I'm just honestly, inspired by so many other great scientists and science communicators that have come before me and are still active, that it's just wonderful to be part of this world. And I know I get so many kind letters and people in the comments saying lovely things about the impact it's had on them. I remember the other day I was at a meeting in Italy, and this girl came up to me and she said, "Oh, I'm really inspired by your YouTube work." And she's a scientist. She was a graduate student. And she said, "I actually became a scientist because of your YouTube videos."
That's pretty cool.
I was like, wow, that's, I never thought that would happen. But the fact that if I've made even one new scientist, that is like, I've done my job.
Yeah.
So that's huge when you hear things like that.
What's a discovery that you would love to make in your career?
I think life. Yeah. I think the most realistic thing I could hope for is the detection of microbial life on another planet. Obviously, if we detected an advanced civilization, that would be the absolute pinnacle dream. If we got like a mathematical sequence of prime numbers coming down a laser beam directed at the Earth, and within that was embedded the encyclopedia of the galaxy. I mean, that would be like the absolute dream thing to hope for.
If you found a planet with life on it, do you get to name it?
You get to name a planet in principle whether it has life on it or not if you find it. Usually astronomers are very conservative and we just name the planets after the star that they're around. So the stars usually have names, and it's just like a catalogue name. So if it's the 1000th star that James Webb has observed, then it might be called like James Webb 1000 or something. So you just normally call the planet like, okay, it's James Webb 1000/B or something. So we're not very imaginative, but there has been a movement to try to get the public more engaged with naming. I think the IAU has a project, if you Google it, IAU name exoplanets, where the public have submitted suggested names, I think, for the first 100 exoplanets that were ever found. And those are now canonical. So the first 100 now have proper names. I think like HD 209458b, for instance, is now called Osiris. So it has like a much more easy name to remember. So I think there's a movement to do that, and it's cool. It's a nice piece of outreach as well to get the public feel like they're involved, because these planets, I mean, why should the scientists get to name it? Yes, they discovered it, but the telescope is not their telescope. Like, you paid for the telescope with your tax money. So if it's funded by the public, I think the public should have the right to call these planets whatever they want, even if it's Boaty McBoatfaced, whatever they want to call it. I'm okay with that because it's their world.
Yeah. Awesome. I've enjoyed this conversation. You can go on and on about all the different areas of space, but we'll call it a day there. Where can people find you?
Yeah, you can head to my YouTube channel. That's Cool Worlds Lab. So at Cool Worlds Lab. I also have a podcast called the Cool Worlds Podcast. And you can find me on Twitter and X at David_Kipping.
Amazing. Thank you.
Yeah, pleasure.